Sorry, I wasn't in touch. It was so busy.
That's fine. No worries. Yeah, it's great. Have a chat.
Close the store or?
Oh, now it's super dark.
Is this too dark?
It's maybe a little dark.
It's a little bit.
Probably won't be able to see.
There's not much I can do. I can do that.
Is that going to take
No,
long? So that's
just
too
leave-
much.
just leave the
If
door
we leave
dark.
the door open, so then we can still see people.
Just a little bit low. Want to get the light level.
That's as exactly right.
Stop this.
Okay. Are we good to start?
It's already
Okay, good, awesome. Welcome to another SensiLab forum. I'd like to welcome Alisa Andrasek. Is that how?
Yes.
Sorry. Alisa has come from RMIT today, but she's recently joined RMIT from the Bartlett in London. She describes herself as a designer and innovator working at the convergence of design, computer science, and exponential technologies. So Alisa is bringing AI and robotics to the forefront of architectural design and construction. So today she'll be talking about some of her recent work, which is high-resolution structures designed with algorithms and built with robots. So I'll let Alisa introduce her own work in, I'm sure, a lot better detail than I. But if you'd like to join me in welcoming her today.
Thank you, Lizzie, and thank you, John, for inviting me. I'm very happy to be here because I'm in Melbourne since recently, and it's really nice to see a research community. So, as Lizzie mentioned, I've been doing a research at the convergence of some technologies, especially computer science and design and architecture and construction for the past almost 2 decades between New York at my research work at Columbia University, our Architectural Association Bartlett in London, and finally now at RMIT in Melbourne. So just to quickly introduce some of the theoretical premise of my work, just very briefly, before I actually focus on some recent examples of the work. So when I started my research, the main question, the core question was, how do we address complexity heads-on in design environments and constructed ecologies? Because for me, it was the most important thing to address. And somehow in my work, I decided very early on to focus on a kind of informational structures at the core of the work, because to me it looked like that was the connective hinge for everything else. And of course, the idea of computation and expanded capacities of computation was at the core of it, because I think never before in the history we were able to compute, design, and construct at the resolution of specks of dust. This was never possible before. So for me, that kind of increase in resolution of computation was incredibly important. And also sometimes I decided to, even though in my early education I was educated almost in a kind of modernist tradition in Croatia when I started, but at some points I decided to forget almost some parts or unlearn some parts of architecture and design history, and to look at the first principles. How do we engage with physics directly, with in this case computational physics, or certain first principles that then allows us to rethink what we are doing. And I also often talk about this kind of, if architecture has one superpower, it would be the power of complex synthesis, because historically it has a long tradition of bringing together, binding a plethora of agencies, whether it's current modes of technology and construction, or mode of the time. We can go into any period of architectural history. For instance, Gothics is a very kind of famous one. The intersection of certain elements that were happening of the time, and then architects coming and as a kind of this idea of global or complex synthesis. So this was the core of my interest. I started looking into, I just mentioned some of the ingredients of my work, computational physics a lot. We see in many fields now, for instance, in the car industry, such as McLaren in UK, designing Formula One. So in the past, you would have to prototype these pieces, and maybe you would design a couple of pieces of this car. It would take you the whole year. Now, every couple of weeks, we are designing a new pieces because we can simulate not only how this car runs in a kind of wind tunnel with another cars, but also exact physics of particular materials connected to material science. So this idea of binding micro to macro conditions is very important for me to do it explicitly. So we can really design in this sort of resonating complexity of ecology rather than just working with metaphors, which has been a case in architecture for a while. And so, as I said, what I call the fabric of architecture relates to this kind of idea of the constellation of interrelated contingencies involved in the formation of design and architecture. And as I said, I put resolution, increase in resolution at the core of it, because if we are looking at the way nature builds, or recently we see lots of advances. After I don't know how many years of computer scientists trying to evolve artificial intelligence, that research was very slow. But in last few years, we see a certain acceleration afforded with these increased volumes of computation. So for me, the resolution somehow, very early on, intuitively, I felt like this is the key element. Looking at the acute technology and also at the natural systems. And anyhow, for instance, this is what I often, often show, because the other day on Friday there was a presentation of 6 international architectural offices here in Melbourne for the tallest tower in Australia that's supposed to be built in South Bank. And still we see that certain modernist paradigm at play that operates in this resolution that Rem Koolhaas, who is a kind of the prime representative of architecture, today talks in terms of the scale of escalators, doors, walls, ceilings, etc., toilets. But to me, the new fundamental, the new fundamentals of architecture, or fundamental building blocks, are actually going directly into physics and into much finer resolution. And how do we then reoriginate design from that point of view? And the way I always work, I wear multiple hats. So I have a different. I help spawn some startups such as AI Build. I will be showing some of our work later, or my own practice BioThink, which I started in 2001, or my research lab in London was called Wonder Lab. Various other operations, my curatorial activities, always trying to somehow one facet accelerates another. So. So even when I started my practice BioThink, this was the idea: how do we look into this computational core? And at the time, people sometimes think I'm doing biomimetics because my practice is called BioThink, but in fact, not at all. I was only fascinated at that time in 2001 when I was trying to find a model of complexity. I was looking at how information spreads in biology, and to me, it looked like a very advanced model of information, trickling information through a complex system. That's why I started calling my practice BioThink. And there was one tendency, if I could single out one feature of my work over the past 20 years, it was a constant discretization of informational structures at the core of it. So it started with what is now very popular in architecture as parametricism, the kind of more linear functions, and always deconstructing building blocks through more and more discrete algorithms in order to work towards adaptation and being able to bind multiple systems, not only systems of abstraction, but data that is outside of it, and how we start synthesizing. I won't go into all these examples, but I will just mention some major categories. So multi-agent system is one of these algorithmic groups that I worked on quite extensively in many, many examples. And I will just quickly go through a couple of applications, for instance, just to demonstrate how we used it in design work. In this case, at the scale of architecture, this was a big competition for a port terminal in Taiwan, so a 350 meters long building. And I wanted to work with certain elements of local weather, and so it's a kind of tropical climate, and I wanted to increase the circulation of air, physics of air to the building. But I also wanted to create this sort of idea of when you are passing through the building, you are going through these different, radically different environments, so you have almost parallel realities of different environments. So when you enter the building, you have this big wave crashing into the facade, and all these surfaces that you can see like this was abstract model, were done as the idea of working with certain constraints of construction. In this case, we were working with this Austrian company, Reader, Fiber C. They are probably the most advanced company in the world in terms of doing glass reinforced concrete facade panels. They worked with many architects like Zaha and others on demanding building skills. So one thing they told me is that I can have every panel different as long as the underlying structure carrying it remains or contains the kind of horizontal datum, so it doesn't X and Y, let's say, dimensions can shift, but Z not. So then I programmed the multi-agent system to work with that simple constraint and to work on these panels, because one of the concepts of this building was also that the cliffs, when you're entering Kaohsiung in Taiwan, they are very iconic, and the client wanted some sort of iconic element. And I also wanted to see how far we can push, when we are working with the modes of construction, how far we can push in this kind of geometrical complexity of these elements. So then the agents produced something like this, and at the time it was also very difficult. This was maybe 2009 or something. Difficult to render this stuff, but I thought that only if we actually prototype and build them, we can see the weirdness that one experiences, because there is this kind of constraint, mathematical constraint in the fabric of these tectonic elements, and yet there is something that resonates complexity found in nature, such as natural cliff formation. And then another application in this building where multi-agent system was used was for navigation, because this was a terminal building, and I just thought about this type of buildings such as airports or different type of, like in this case, a port terminal, and usually people go and follow the signs in order to find certain gate and things like that. But to me that seemed very mechanical and somehow with reduced complexity. So I started looking into, on YouTube, when you look at this kind of slowdown of lighting, and then also I was reading about this amazing bioluminescent population of these insects in Africa, so that when the storm is coming in, they start to glow over the tens of kilometers of landscape. So there is almost a layer of artificial weather, or not quite artificial, but there is a certain event at a very large scale. And I thought, what if we complexified it, instead of having these mechanical on-off switches, if we complexified the lighting conditions in a building and developed this kind of connective tissue through these bridges at a very high resolution of structure, but with embedded lighting. So when someone enters from one of these big boats, it would kind of more intuitively follow the landscape, follow the emergent glow through the structure, through the fibers of the building, and we can think about lighting in the building at a higher resolution. So this was a kind of just conceptual work with that concept. And then another quick application of multi-agent systems where I was working with a few buildings. In this case, it was a larger project, which I will not go into many algorithms for use, but it was an urban development for a very prominent location in Dubrovnik. I'm originally from Croatia, so Dubrovnik is this beautiful historic city, town at the coast. So this site had amazing views on the sea and the old town. So I was thinking, but only in front of the site. So I was thinking about this kind of urban villas that the client wanted, and I thought that in this case the luxury is really to maximize capturing these views and sun. And also I was thinking, if we think about the patterns of living in this area, of people in this region like to be outside, like to be on the sun, so you want as much exterior areas as possible. So like if you're thinking about, for instance, fractals, Mandelbrot, for instance, looking at the coastline, and you can come from point A to point B in a very straight way, just drawing a straight line, or you can look at the coastline and increase this line. So that was the concept of increasing the facade sort of area, opening more windows, more views, and agents were programmed to actually capture some of it. So here we see something else than a kind of simple parametricism where we just have like a linear function scaling certain elements. Here agents are seeking and negotiating between many elements. At the time I was also thinking, okay, apart from these views and trying to maximize shredding of this typology, I also thought, and I don't know how many people here are familiar with Peter Eisenman, architect, but he was this was an architect that worked in a kind of deconstruction period, so he was very interesting with sections, and I thought picking up a certain language of these very shredded sections, and then this culture of Mediterranean living, how we program it into multi-agent systems to search for different results. And then in the next project, which was actually just in Montenegro, the next door, there was a project for a small tower and the same criteria. So we were, in this case, different building typology, but the same behavior. So the behavioral pattern or algorithm was just transmitted into this problem. And what I said very early on in 2001, when I started my practice biothing, I actually made a statement that not only via learning and evolving through the exposure to this type of algorithmic design processes, but also, and maybe even more importantly, one could argue it is learning. So through every next project, these algorithms also evolve. And only now, when we are getting to the kind of machine learning slowly making its way to design, we are actually getting to the point where we can quite explicitly work with some of these ideas. So it took almost 20 years, but hopefully we can do more now. And let me just go through just one more macro example before I go into what I think for this audience will be much more interesting micro examples of this type of work. And this is really macro example because this was an invitation by Kengo Kuma, Japanese architect, and Tadao Ando to develop an urban proposal for Osaka, and this was a very large site. I should just try to find one of the renderings. Yes, okay, here it's a center of Osaka, and there is a bullet train station. It's really it was a very long brief, but one thing that stuck with me when I was reading the brief was that the 2.5 million people pass through this site every single day, and I just could not somehow fathom this number, because even through the whole central London we can barely claim that 2.5 people pass through. So it's an incredible density, and the only way I was able to think about this kind of urban density was to think about this stampede of crowds of people and different uses as a river of people, and I literally blasted the site with computational physics based on site data, specific one, where the people are coming from, at what time, and trying to actually derive through physics of liquids how to organize this urban plan. So something started emerging that started looking very much like desert dunes. And then I was thinking, well, I don't want to have a desert dunes in the middle of Osaka. This is not Middle East. Somehow not a good idea. But then I started thinking about the whole manga and anime culture and how Japan has this special relationship with unnatural or kind of after Hiroshima and Nagasaki, in the cultural fabric of Japan, we find a lot this kind of relationship of nature and unnatural. So I started thinking about some otherworldly desert dunes, and I spent, in fact, it was a very precious time because we only had 3 weeks to design this project, and I spent the whole week staring at Mars dunes, trying to pick up some otherworldly quality of this. So we eventually modeled actually this massing, but it was based on the data from physics, and it was inspired, let's say, by the weirdness of different physics on Mars, because I thought it has to be otherworldly. But in fact, all the organizational flows and lots of program, because these are 7-floor tall buildings, basically, it's an urban massing, so you shouldn't see this as architecture, this is just planning of where programs and buildings go. And then also I work with 2 big engineering companies. One is Bureau Happold, one of the biggest engineering companies in the world. The other one was Hitachi Consulting, which in Japan, which was looking very much at future programming of this type of sites and what are these kind of users, how they behave, and what are the and Internet of Things and all of this. So we thought about many new technologies, and obviously we did lots of crowd simulation, but I was also thinking what kind of structure at a high resolution can actually mediate such a complex site, because I've seen it as a field that could be reprogrammed, because we were coming up with programs such as these cloud offices, the fact that now we are working less and less in a kind of permanent offices, and everyone is on the move, especially on this site, which is the biggest node for, I think, Japanese and Asian business kind of users coming by the site. So the idea of cloud environment that could be reprogrammed was very present. And then I started looking into some of these megastructures, the historic examples at a low resolution, and thinking how can we develop something that is high resolution and more heterogeneous. And engineers were calculating all these people passing through the site, and I think we had 7 or 8 ways of producing energy on this site, but one that was most interesting to me was capturing vibrations, because when 2.5 people are passing through this site, you actually get a decent amount of vibrations, in fact enough to power majority of this site, and with the 7 other forms of generating energy, it would power even surrounding buildings. So I started looking into some simple algorithms, quad trees and things like that, to map where the structure needs to be densified. Then we started writing some quite wacky algorithms on how can we develop a universal structure that can grow anywhere if we just give it certain conditions. These were just some primitive prototypes of protostructure, not yet applied to the site. And then there was a question of working with quite big data of this sort of physics flows, and how can we start to instantiate different sequences of this structure. And sometimes it was just a kind of shell, but sometimes it was really the forest of cloud-like structure. And then all the other programming of systems on this site, whether it was, for instance, and again, don't take this as architecture, but this was just a kind of diagrammatic rendering of how this site would be reprogrammable in terms of different events. And I even had a swarm of robots crawling around as urban pets and cleaning this site, and then the water conditioning and all of this, so how lights, obviously, Internet of Things elements. We had lots of discussions of how all this, how this becomes like an urban operating system in a way. That's how Bureau Happold called it. I thought it was a bit old school to call it like that, but maybe, but anyways, it was the concept that it's highly reprogrammable urban field. And then in many of my projects, as you've seen in one before, I have this kind of canyons almost, and like a signature element. Anyways, this one also had these shortcuts to the site. So this was, but then of course this is more what architects do in general presently, which is yes, we are using some technologies for planning, but how do we materialize these structures? How do we go micro to macro again? Because construction industry, yes, this was a recent, relatively recent, last year cover of Economist magazine, and obviously Trump as a big disaster on the cover, but another big disaster is construction as the least efficient industry in the world, and one of the biggest ones. So really it's stuck in the 19th century and earlier methods of building, and very hard to change. And with all these technologies coming up, the question is, how do we build differently? How do we materialize using all this knowledge that we never, and resources that we never had before? So for the past 5 years maybe, I was quite focused on actually robotic construction in convergence with algorithms and all these other technologies, and trying to prototype one-to-one some high-resolution microstructures, you could say, that are at much higher resolution. And of course we see everywhere, in, as I said, in nature, so this is a very obvious example. If you look at our bodies, so fibers of collagen, they pattern in a certain way, and you get the strength of the bone, and even obviously when you look through the microscope, it's a different patterning at the bottom of your leg, where you have more weight versus some other parts of your body. And so and then when these fibers of collagen texture, so the same monomaterial, but reorganized at a molecular level, you get elasticity of your joints, or again even larger elasticity of your skin. So all the same material, just different at high resolution repatterning of these fibers. So this kind of idea that information is becoming more and more free, or let's say you can get it for free, soon will be completely free, but material is precious and expensive. This is what we see in nature. There is a very intensive computing of physics at a molecular level, and then the design, I mean the material condition arises through this intensive computing of physics, biology, etc. So how do we start working on that level? And I will just show a few examples from the research along those lines. For instance, in this case, we were looking at multi-agent systems. For instance, this is a simple chair field prototype. So running agents in a way to develop, conditioning them in such a way as to develop certain zones of this chair that are reinforced, that are stronger for the structural purposes. And then voxelizing that data, because this is not geometry, it's just the data like map where structure should go. And then voxelizing some of that information, and thinking, of course, if something is interfacing your body, maybe it needs to be higher resolution to be more comfortable, or sometimes you need denser sequences of structure. So you can control now design with that kind of resolution. And then thinking, okay, so how do we print it with robots, with particular method of 3D extrusion, robotic extrusion, so developing printing paths, and in this case, for instance, again, the wall, working obviously with the voxel space at multiple orders of scale as well, to different densities, working on some little local transfigurations of voxel grid, so the tricubic interpolation in this case, to get some other type of microstructural textures, and then combining these different elements very locally, so you can get these different sequences, and then running some proto designs. So the idea of lightweight structure that is light yet strong is very interesting to me. And of course, this type of highly intricate structures are always, they also have a power to be heterogeneous. So again, not a linear function. We see in lots of current architecture, we see a wave function over the facade that just scales things from big to small in a kind of linear gradient. Rather than that, how can we, because I think every building has is a heterogeneous condition, how do we acquire some powers to produce this kind of heterogeneous ruptures? And we've seen on Friday lots of this kind of aspirations. So how do we, for instance, open the tower typology to be less rigid, but then we see collaging. There is no application of certain tools that would really develop morphology of the building or architectural fabric that can rupture to radically different states. So this is what we sometimes try to do. And in this case, similar, but taking, for instance, computational physics such as fluid dynamics, and in this case we splashed it around the body, so it wasn't designing a chair by modeling it, but again taking a virtual body and splashing the physics around it and getting certain fields wrapping around the bodies and data fields, and then again going with the process of printing extrusion with robots, so we can these also in London we would build our own nozzles, so they're quite rough but they somehow work. Students would build their own nozzles for robotic printing. Or this is like almost 3 meters tall column from the same system or a different algorithmic system, but again lattice. So this was incredibly light. I can't remember exactly, but at the end I will be showing one of the recent projects and you will see how light these structures are, and yet surprisingly strong actually. Another example where we worked with noise, with computational noise, in this case Perlin noise. I love noise and I like, it's very hard to design sometimes with it. My students always complain because they feel that they don't have control because noise is destabilizing their preconceptions, but I love working with it. And thinking about this type of fabric of architecture, if we could really design at this resolution, this is a prototype of a column or a few of them. And again, in this case, this is different than the previous cases because when we had, oh, this is not good. Let me just do this so I can actually see where I am. When we had something like this, it was based on a certain ABC, whatever, certain states within each cell. But in an unstructured, noisy field like this, we don't have that sort of prescription, so we have to use other algorithms that are kind of pathfinding through sea of data and trying to find a kind of optimal printing paths, which is much more difficult, but then you get this kind of samples, and if this is a kind of microstructure that is highly heterogeneous, and how you can start working with the structural properties but also aesthetic properties, how the light, potentially heat, goes through the structures. And also something that is coming more and more, which is automation, and in London we did a little bit with that. With deep learning we looked into, for instance, teaching a robot what the node is, so after 10,000 times when you point, poor humans have to point, okay, this is node, it eventually learns what the node is, which is then very efficient because it can see exactly, because obviously when you're extruding with this type of material, the material noise and tolerances accumulate very quickly, so what you actually design has nothing to do with what's happening in real time. So this is very helpful to computer vision and in this case deep learning to find exactly where this where it needs to print. It also accelerates the printing process because it just snaps to the nodes. And incidentally, also the project I was just showing with the noise is on the cover of a recent book by Mario Karpov, who is a very well-known theorist in architecture, talking about this kind of second digital turn. And what I was briefly mentioning, I won't go in depth into this here, but change in computational models, not looking at linear functions and mathematics of continuum, but going into more and more discretized models of computation, because in my experience, since I started, for instance, working with agents and other algorithms, we can adapt locally to other systems. So we are not covering everything with some linear, static, mathematic blanket, but we can actually bind these computational elements in a discretized manner, and this is more and more the case. And then I worked with Andy Lomas, who was a part of my research lab in London, and Andy is great. I think Tom here knows him also very well, but he has a very rich history. He directed some of the special effects of some of the most famous movies, that such as Matrix and Avatar, I think, and others. But then he also has his own artwork, which is brilliant, and he's also a mathematician. So it was fantastic to have him on board. And we were both very much interested, because for years, whenever I'm working with these systems, how do you search to it? And if you have only a few parameters, it's fine, it's still legible for human cognition, but when these parameters grow, it's very hard. It's almost like diving into the ocean, deep ocean, and trying to unearth some pattern, recognize some special creature or something, and it's very hard to find for human cognition. So how do we even probe in this sea of data? And we were both interested in that, and we did different experiments with it, but the idea was to design a system, you could say, or that would search through it, and I will come back to it in a minute. So in this case, this kind of a series of research was looking into cellular division, which started as a collaboration with Andy, who wrote the initial algorithm, and applying it to different orders of scale in design. And we also, with our own kind of custom-made nozzles, we would also try to sometimes print in multi-materials. In this case, it's a prototype just in different colors of polymers. But sometimes we would print with, for instance, combinations of wood and polymers, or carbon fiber and similar. Why is this not running? I don't know. So this is one of the examples done with a. Oh, I didn't want sound, but I can't control it now. So this was done through cellular division algorithm, first developing this abstract behavior, and then being channeled into design of a kind of protocol, so just a chunk, generic chunk of architecture. So this is already like 5 million cells. It becomes challenging to compute as well, so we started working with GPU and CUDA-based computing a little bit. Because most tools that architects use are unfortunately only working for a single processor, which doesn't give us much volume of computation. Here also in this system, something starts almost like a crystal, subdividing this kind of polygonal faces, and then when it reaches certain resolution, it becomes very much a biological model, or suddenly organic, more organic in its nature. And to me, that's beautiful, this kind of transition between crystalline nature and then biological. This is the kind of nozzles that we would do ourselves. So this is just the working process. In this case, with multiple feeds material. This column has been exhibited at the Pompidou and ZKM in Germany and some other museums in Europe, and it was 2.5 meter tall, just printed with this kind of our own nozzle, designed by cellular division. Almost no cost apart from sampling from material, because it's reaching bigger scale. And so some other examples from the same research, and in fact here solid division, like in the previous example, is used in a 2.5D, you could say, because it doesn't explore all its dimensions, because it's adapted for layer by layer printing. So it only works, maybe we will do, see that here. It only works through solid division in a kind of planar level, in splitting these strings in different resolutions. So you put some nutrients in certain areas and they start splitting more. So you get a kind of heterogeneous densities in this fabric. Here. Also, you, for instance, start looking at constraints of fabrication, because when you print with different materials, for instance, if you're printing with plastics, you have 45-degree possibility of cantilevering layer by layer. If you're printing in clay, you only have maybe 19 degrees. So depending on the material, the geometry has to adapt as well. Here we see also this type of differences in densities, etc. Applied to furniture in this case, but previous, and then with Andy, because he developed Species Explorer, we worked with some forms of supervised learning, very simple initial states where we would evaluate certain results, 1 to 10, give it certain rating, and then trying to find more of the successful ones. So just the kind of first steps in this kind of design assistance, but within a design search, some sort of little accelerator. Another, this we done in Melbourne last year, just some pieces of urban furniture, the same algorithm, a little bit further reduced again for the purposes of this particular design. So with robots, we just printed some of these, you can see them at our MIT, they're maybe 1.2 meters long benches. So, and in this case, we see the same, exactly same logic, the same algorithm, but applied to three-dimensional condition, or obviously then temporal as well. So, adding more dimensions. And this research was based on thinking about 3D printing of concrete. So, initially, we only researched on the surface conditions that are quite high resolution and heterogeneous. But then later on, we started going more into the depth of the printed tissue, and this might show a bit later, and trying to think of more porous and lighter concrete structures. And in these processes, we always develop custom written tools that, depending on the project, what actually needs to be handled. So they always bespoke to the problem. This was some of the porous concrete ideas. There are lots of issues with printing concrete, obviously, because the tensile force is similar, so we need to work with material science to get further. Here as well, we used Species Explorer to recognize different patterns. And so this is one of the more recent projects which is based on some of this research. I was doing a Croatian national pavilion for the Venice Biennale this year, and first I designed something that had 500,000 voxels, always being greedy about the resolution. But then the printing time only allows us, the printing simulation allowed for 40,000, so I had to go down quite radically. So in the end, I designed this rather than that. But anyways, it was still probably highest resolution piece at the Patricia Maher was saying it's definitely the highest resolution piece at the Biennale. And even you see some of these structural simulations really analyzing cells, so almost looking at the microscope in some biological tissue. Printed again with the AI Build, which is the startup that came out of my research lab, and extrusion of polymers. So this was maybe in the end the field was 8 by 8 meters. I don't know, bigger I guess than this so that piece was so 8 by 8 and 3.5 meters tall, quite massive chunks of structure. It was only 275 kilograms, which engineers are telling us belongs in the category of lightest structures we can think of to cover that kind of area. So the only other way to build so light is using some fabrics. And yes, this is only polymers for now, but this was incredibly strong. So everyone at the Biennale was shaking it and trying to see whether it will collapse. But no, it's actually incredibly strong because it's a very distributed structure. It's based on multi-agent. Let's start here. Sorry. It's in this case it was we started designing with noise, but then because we had such a limited number of voxels we were able to print. I changed it into multi-agent systems to make it because the initial idea was mathematized cloud. I wanted to have a sort of, I was looking at the clouds, I was actually flying over Queensland, there were these amazing clouds and sun formations, and I was thinking, okay, this is the project, we just voxelize this and we have a project, just put some movement maybe with physics into the clouds. So we started designing that, but there was no enough printing time. So in the end we designed these agents that are just going, they're swirling as they go from bottom to top. They sort of spiral almost like little tornadoes, and when they come to the ceiling then they start negotiating, so they develop this type of structure of columns, and it also, because of the directionality and counter directions in these columns, the structure is stronger than it would be with generic voxels. So this was quite large piece, and I'm hoping to show you something much more impressive next spring here in Melbourne, and done in real materials at a bigger scale with metal 3D printing. So we will really go into maybe a chunk of the building that is a real structure. But this was a good kind of prototype to give imagination to people what high resolution structure might be like. And we can imagine, again, as I was saying, transmission of light, transmission of structure that is lightweight yet strong. This one 270 kilograms, but when we start printing with different metals and with different densities even of spraying of metal, then I mean the level of data, but also the intelligence of this structure will increase many times over. So. And I think buildings currently, according to laws of physics, rough laws of physics, they are roughly, typically 10 times at least heavier than they could be. So I think there is lots that we can do in a kind of building fabric that we have today. And our students are now designing these proto towers that are really working with physics of wind. For instance, in Melbourne now, for the first time in my life, I live in the tower, and wind is incredibly loud. And one thinks if one could disperse, because that is also the major structural pressure on the towers, the wind, when you have tall towers, because the geometry and the morphology of the built fabric is not working with non-linearity of fluid dynamics like wind. So now we can actually do that, and we can also envision in a very near future, and hopefully I show you already a chunk in March, we can build that in architecture. This was another speculative project. Maybe I will close up soon because I think these chairs might be uncomfortable. But in this case, we were working with stigmergy behavior of again multi-agent system, but based on stigmergy. You know, like these ant colonies where they are signaling with pheromones and building this kind of termite mounds, and I was always fascinated by those because of the way they transfer, for instance, air in this high resolution structure. And students were looking into that, and then maybe I just run the video here. Is this running? It's thinking of running. So we were looking into the idea of 3D printed thick skins for architecture, because, for instance, the regulation for building skins in Europe a few years ago, they changed, so and they are changing worldwide. So we will have to build much higher resolution. Sorry, this is not really reading well. We will have to build much smarter skins. So we were thinking of how we, and this was somewhere in Middle East, students were sampling light data and how to develop shading patterns in the skin. So initially they just developed something, multi-agent system that adapts to this light data, but then that was too high resolution to 3D print with our extrusion methods with robots. So they started voxelizing these complex patterns from Stigmergy, and suddenly what started to emerge by optimizing this type of printing paths. This is again fetishization of some of this building of nozzles, but so in order to optimize, because you also want robot to print as continuously as possible in these continuous lines, because if it's stopping and starting, it's not a good situation. So through navigating this voxelized data, we started getting this type of geometries, which to me were very Minecrafty. So I was imagining this tower, if you're, let's say, driving in Abu Dhabi from a kilometer away, you see 500 meters tower, and it looks like some weird plant is growing on the, it's that kind of resolution that we haven't seen yet in architecture. But when you come closer, it's this Minecraft almost aesthetics. So there is this kind of, again, the same theme that I was talking about before, tension between something that is organic, natural in nature, and very mathematical and unnatural. So these were some of the schemes for the thick skins that then become also architecture, because they go deeper than just the skin. They become heterogeneous spatial sequences. Also, I don't know if this, if I have it in this presentation, but for instance, these facade panels were based on connection details of generic facade panels that are present in the market. So we only picked our battles in terms of articulation of these shading patterns, and but the connection logics, yeah, it seems like I don't have that. The connection logics were such that between different panels there were these puzzle-like connections. So in a way, the logic that was happening on a micro printing of these complex patterns would also transfer to this other order of scale, when the path-finding algorithm could try to find the connection, puzzle-like connection between different patterns. So it's always, whenever we are designing something, the question is how we mathematize certain problems and how we make them talk together. So this kind of structure of information, which is a connective hinge, has been the feature of my work from the beginning, and I rely on it heavily. I don't even know if to show this one because it's too raw, but I will show it close with it because it's too primitive. But this was one example where, before I left London, the last one, where we tried to we tried to compress somehow the design and fabrication process and automate it as much as possible. So the way it started, the students were thinking about John Forsythe's, this choreographer, dance choreographer. I don't know if you know him. I don't have a video here, but he works with dancers in such a way to condition their interactions. So, for instance, he would instruct them to collide against each other at a maximum speed, or he also collaborated with some architects such as Daniel Libeskind, and so dancers would be bouncing off the walls of the building or something like that. So it was conditioning. It was, rather than prescribing every movement, the choreography was conditioning the field. Very Deleuzian in a way. But we were, students used that idea to kind of teach the robot how to move, to dance in certain patterns. So depending on the movement and the speed and the pressure of extrusion, it will produce these different material accumulations. And it would develop some of these primitive behaviors of extrusion of these fields. And then the next stage was, okay, design a table, but not a human, but a robot. And now I will show you some really ugly tables, but it was just asked, so we mathematized the problem. So we said, okay, first print something like a surface condition, so print in the plane, distribute dents in different ways in this plane, and then through scanning, through some Kinect scanning, 3D scanning, we would pick up some data. Where are the pictures of that now? Of the peaks, and then it will pick up on these red peaks and start building up on them until it builds legs, let's say. So it was completely abstracting the problem of designing a table. And also then the students developed this, so these were the tables that we would simulate through these kind of logics, which were, again, very ugly, but this is not really designed by human, but just us setting up some conditions and letting it make certain autonomous decisions. And also the material contingency, obviously, because when you are working with this kind of very volatile materials, you're getting certain qualities, but you cannot precisely control what's going on. So then students prototype some of these very noisy things. And also, okay, I won't talk about this now, but so the software was developed to fluctuate between this noisier type of dancing and more controlled and then instantiated in different problems of make a wall or grow vertically or horizontally, the column. So the desire was to introduce more and more autonomy, and I think I was showing this kind of design search earlier through Species Explorer, and this is still very much our control because we are evaluating, as humans, we are evaluating certain outcomes and getting more of that stuff. But what I was very interested in working on is, for instance, when I'm designing, I'm very particular. As every designer, I'm a control freak when it comes to my own design. So I have a certain sensibility that's been developed over the years, and many other designers, my colleagues, have their own, and we are all very different and biased in different ways. And I was interested in working with machine learning towards first exposing this bastard child of many designers to the process of designing and picking up of certain biases of different designers, and then seeing what it would do. So it gets some sort of ground training, and then see what it would do on its own when asked to. And so eventually it should be really a conversation. I had some talks with the computer scientists in London at UCL, and people related to DeepMind as well, natural language programmers and things like that. So they were asking me how I work with students, and often, especially in London, I was directing a very large postgraduate program in architecture, and over 130 students, and around 85% were from China, and many of them were not really speaking language so well. So trying to work with quite complex ideas, and I think there were lots of methods that we developed how to work with students to help them very quickly engage with abstraction and design with it. And scientists were very interested in how we work with humans and how we could potentially train the kind of machine learning instances to so this other type of cognition coming in, how to work with us, and I thought that was a very interesting problem, and I still want to pick up on that in the near future, because I think this kind of synthetic cognition between us and between that other thing and what happens in the space in between, or especially what happens with that kind of new cognition, I think it's very interesting. And so let's see what happens, and maybe some of you are interested in collaborating with us on some of these next steps. So maybe I just close here. We'll talk till tomorrow, but I think the chairs are probably.
Does anyone have any questions?
Yes, if you have some questions.
Yes. I'll ask a question. So you talked about a tension between mathematical structures and organic structures, but it seems to me there's a tension also between control and because all of these things are emergent properties, right?
Yes.
So you're, I guess, you know, when we look at natural beauty, that's an emergent property of various physical processes operating on a molecular scale, and that's kind of, you know, you're drawing on that strength. But at the same time, you're now sort of flying by wire, because you're some distance from the final form in the way you control what happens. So I wonder if you could sort of talk about the tension. You talked about being you know, I think you said a control freak, but I think that's not. I think probably you are more comfortable, you know, giving up some of that control than many architects. Right? So where do you sit on that tension?
That's a very good question, and someone like Pia Edney Brown, who's a theorist and architect here at RMIT, wrote about this issue many years ago on the example of my work. So she was comparing it to working with something like a little dog or some sort of that you cannot absolutely control. This is a living organism, it has a will of its own, but you can guide and steer and train it. And yes, I mean, now, for instance, the other day I just to my new students here at RMIT, I gave them this algorithm of Perlin noise, and it was noise at different resolutions to design these towers, and they told me, this was the first thing they told me, but we don't have any control over this design process. So and I said, yes, I know, you are used to do this one-to-one, you imagine something, and this is how architects work or designers for many centuries, and then you draw it from your head, and this one completely destabilizes you, because in general, I mean, generative design in general, even simpler forms of it, you set up certain conditions and certain code, and then you run it, and there are certain emergent, as you're saying, conditions, and then you have to capture it and run with it and really collaborate with it. So the agency is already distributed in a kind of simpler generative processes, but when you get to working with things like noise, multi-agent systems even, and not to mention now machine learning, and where we absolutely have no idea what's happening within neural networks. So but I really enjoy working with this kind of thing, and it's almost like a pattern recognition, but it's running, and this is what Andy and me discussed quite a bit, it's running out of control in terms of that our human cognition is not enough anymore to recognize these patterns, because the amount of data is so huge, and so that's why we need help. We need to develop design assistants, so this collaborators more explicitly, and I'm very much...
So the collaboration is not just between humans, it's between humans and this kind of process.
Yes, and my entire work has been actually done in that way. I mean, for many years, in one form or another, it's always collaboration with, whether it's with material system, with we did this, this will be again shown soon in NGV. It was already shown in Melbourne. I'm hoping, since I'm seeing it, yeah. This was a very simple, maybe simplest project I ever designed, but initially it was developed many years ago when I was teaching at Columbia, maybe 15, 17, 18 years ago, when I was trying to teach students rule-based systems. So instead of dropping architectural students and never seeing code into huge abstraction and then they freeze, I tried to develop some friendly making by hand exercises. So one of them, the rules of this game, was design a component that has certain levels of connection. This one, for instance, we eventually designed this for London Olympics, but it has, in this case, we have 3 possibilities of connection, so only 3 vectors, 3 bidirectional vectors, sliding ones. For instance, they could develop connections that rotate and things like that, because I wanted them to understand the logics of vectors as well through this exercise. It was basically subversively teaching our students maths and basic and programming. So this is one component, but every time someone plays with it, you get different results, and it's been now in 30 countries and in many contexts. It's all one component because of the...
I did give you work.
Yeah, well, you will get a chance soon at NGV. They will set up one room because they acquired also. It's in many museums as well. But because it's produced through this kind of injection molding, so we can produce 10,000 components in a few hours. So because of the production model. But for instance, in this video, these are students that never worked with this system. Apart from what you see on the right, this is what we pre-designed as some sort of fixed elements of furniture. But what they are assembling, these structures, they just came up with it and they're just playing. So there is no drawing. It's just emergent kind of through play. The design happens through play and the energy of construction comes through play. So it's completely emergent, just one component, many, many different outcomes. I'm just trying to find some, kids always try to, I don't know, armadillo, butterfly, weapon, or these guys, we were like, but we designed this as a, people always try to assign meaning to these things and some sort of figurative things, which we didn't pre-design it for, but it's quite universal. So even this is completely out of control, and then we donated it to some schools in London, again, to subversively teach, train the army of people that can code from early on. But in this case, this was some siblings and their mothers said, wow, this is so great because they are always in front of the screen, they never talk to each other, they're just playing games and stuff, and this is the first time that they were like collaboratively doing something outside. So yeah, even this guy made a friend. So I mean, even in this case, a super simple example, just the building blocks of very primitive logic, the principles are always the same, so you really picked up on this. So obviously I'm very keen to expand this other cognition and how we train and what kind of results we are getting that we couldn't get just deterministically designing. So please, let's collaborate.
Yes, so maybe a sort of flip side to Tom's question is there's been a big discussion in generative art about what's called algorithmic genericism. So, you know, in architecture you saw the sort of Voronoi movement. So architects discovered what Voronoi partitioning was, and then suddenly it appeared everywhere.
It originated here in this city.
Yeah, yeah. Yes, in architecture, not the actual original mathematical.
Yeah, of course.
Yeah. But you seem to have sort of successfully kind of escaped that. I'm just wondering if you had any insight into how.
But that's interesting because you obviously know Roland Snooks, who worked with you guys, and he was our student at Columbia at some, like long ago when I was teaching there, and I remember showing him because at one point I was curating in Beijing. I was curating some show of architecture, and there were 50 best schools in the world, and I think every school had a Voronoi project, and I showed it to Roland because at that time he was coming from Melbourne. He was big time into Voronoi, but I myself also used Voronoi because, but mostly as a logic, not as a geometry, because it's obviously very good logic to deal with the different densities. So if you have a point fields that have random densities, for the meshing or for the kind of subdivision of space, it works wonders. But then I would usually just use it in an invisible way as a logic that is then just a field for something else to grow.
Yeah, I guess it's sort of a deeper question about algorithmic aesthetics. So how much of the aesthetic comes from the algorithm? And if that algorithm is something that everyone can do, what is the role of the designer in doing that?
Well, I mean, that's another thing. I had a discussion with some of my colleagues, and yes, many you could call algorithm designers, or they take a raw algorithm and just run it, and this is a raw kind of aesthetic. I'm maybe one of the most extreme ones that spend most of my time on design search. So I inflect it. I'm very that's why I said control freak. But in fact, I really enjoy. I actually spend most of my time less on writing algorithm, more on searching through it for possibilities, and more on synthesis of different algorithms. So I rarely work with one logic only. it's usually a synthesis of quite a few, and that sort of complex synthesis, and that's why I was always going into more and more discrete computational ingredients, so we can bind these logics at the molecular level. So I'm very biased in that way, but I think that also helps in this next phase when we are thinking about training and learning. I think design search is becoming so opaque, and I think my experience with that could help potentially in this next phase of training this inhuman cognition that is supposed to emerge. And I also, maybe this will sound naive and romantic, but I told our computer scientists that I met at UCL, I told them, well, if I can in some little way contribute to this emergence of this new brain, and if I can, because I spend lots of time searching for this aesthetics of what I call wonder or unseen. So my research lab in London was called Wonder Lab, and it was this kind of search of wow moments. This is actually Andy's expression, wow moment. So something that you've never seen before, and that it really leaves you stunned in a way. And I spent lots of time searching for this, and I said, well, if I can somehow expose it to some elements of beauty, what at least we as humans has this kind of effect on us, maybe that's my little contribution to in development of this new brain. They thought that was very interesting, but anyways, I still need to get deeper into that.
So I'm just aware of time. People might have meetings to go to. So if anyone has any questions, maybe they could discuss it if you're able to stay for a short while. But if everyone wanted to maybe join me in